Hello, can you hear me?
Yes, Chris, I can hear you.
Wonderful. All right. So we can wait another minute or two to see if anybody else comes in a minute or two late, and then I'll give a brief introduction and go through the slides.
Sure, Chris.
Do you have any questions before we begin, though?
Uh, there's nothing more like you built this self parking car.
Yes.
Oh, that's great. Oh,
Yeah. It was quite a bit of fun, but also very challenging. So today I plan to give some introduction on some of the challenges that will be found in both primarily artificial intelligence, but also with control systems in general.
okay. Oh, okay. Okay. Yes.
Okay, we'll wait about one more minute.
Sure, Chris.
But for now, I'll go ahead and explain my background. So for education, I followed a master's of mechatronics in the United States at the New Jersey Institute of Technology. Then I did a one-year master's program in embedded systems at TU Eindhoven in the Netherlands. And currently, I'm almost have finished my master's thesis at TU Berlin in Germany under the Distributed Artificial Intelligence Laboratory.
Oh,
So mostly autonomous robotics is my focus. I teach artificial intelligence for Udacity. So I work as a technical mentor and also project reviewer, mostly evaluating code and seeing how students are doing to complete their projects. For this project, the project that I'm going to talk about for the use case, I worked in the computer vision department as kind of like we call it a student worker, because I was a graduate student at the time for Hella Aglaya. It's a kind of a third-party autonomous vehicles company. And that's where we did the self-parking car, which is, yeah, it was a lot of fun. It's interesting. There's lots to be done. So I think by the end of the slides, anybody who is in the seminar or the webinar or watches it later will find that there's a lot of work to do. Other than that, I'm currently working on projects related to autonomous space robotics. So rovers, space rovers, doing autonomous mapping and navigation, sample collecting in space. So I'm doing that through the DLR, which is basically the German space program. I'm working with them through the university, so kind of third party again. But they have an actual physical location at the university.
oh, that sounds interesting, Chris.
Yeah, it's fun. It's great.
It's really fun.
Okay. All right, so I will go through. We're going to be discussing autonomous vehicles in the context of self-parking. So we're going to look at self-parking specifically because autonomous vehicles, you can think, the self-driving car, right? It sounds pretty complicated, but self-parking, right? A car should be able to park itself, no problem. And that's kind of the idea. If we can't get a car or a robot to be able to park by itself without an accident, it's something simple sounding like this, then we're not going to be able to have fully autonomous vehicles for a long time. So let's look at the motivation. First off, why do we want self-parking? Well, in general, being able to have a car park itself will reduce the traffic delays because sometimes it depends on what country you're in. But so like Los Angeles, for example, in the US, sometimes people are trying to parallel park and they're not very good at it. And it takes a lot of time and skill can be required. If it's a small parking space, they might have difficulty getting in there. Also, we can mitigate accidents because you're less likely to hit the vehicle. The car can do it autonomously, which can also reduce insurance. You have to have certain types of insurance for hitting other vehicles, and you could just allow the agent to be in control of this. And it's also, in general, a test bed for autonomous driving. So like I said earlier, if we can't get the car to park by itself, then we should probably not be driving on the road with the car by itself. So, levels of autonomy. So you might not be familiar with this. Some of the students probably will be. But generally, there are considered, for the SAE, there are 5 levels of autonomy. And this dashed line here, this is showing us it's kind of where we are now. Conditional automation, this would be kind of like the self-driving car parking by itself. So the conditional part is that for parking or other type of adaptive systems, like advanced driver adaptive systems, then the car can transition between the person being in control and the car being in control. Of course, what we want is full automation, where the vehicle is completely in control. But something like conditional automation, this would be lane assistance, and self-parking would be also that. Assisted driver only, this is where you're fully in manual. So this is even looking at not having anti-lock brakes or any other control systems that are in control of the car. So before we started using artificial intelligence, we relied a lot on control systems to be able to dictate how the other systems work. This is a general type of diagram flow. It's from Udacity. What it tries to show is that we have sensors. So for self-driving cars, we have sensors. Of course, everybody's probably familiar with cameras, radar, probably LiDAR, and GPS. We need to perceive our environment. So this can include lane detection or object detection. And at the same time, need to do some type of localization sometimes. For some problems, we can just pretend or hope that we have a map that's provided for us. The map is basically the environment. So if you don't know the environment that you're in, you won't be able to make proper decisions. If the map is given, if you know exactly where the free parking spots are, then the AI problem becomes a lot easier, because you just drive to the parking spot, hopefully without hitting anything, of course. Then we also have planning control. Planning is actually either setting waypoints or the map that you want to. You have this map that you've created or map that you have, and you want to set the waypoints to go to a particular location. And then control is actually physically how we control the vehicle. So PID control, model predictive control, and other types of things. So these are control systems related things. And they usually take place either in the planning loop, it's in the motion controller, the movement controller, or it can be just an external controller depending on the situation. So something like, we'll talk about Kalman filters later, extended Kalman filter, and the control loop might have an extended Kalman filter in it, but also the sensors are going to have a Kalman filter in it. So if you want to make this a distributed system where you can call to a Kalman filter in its own package, you can do that, or you could just put it directly in line with the sensor. So how do we do this? What is the general approach right now? Well, we're going to use computer vision. So cameras are like your eyes. We're pretty familiar with how cameras work, but we're going to need to use deep learning with them. So we need lots of data, big data sets, and we need to be able to teach the car how to distinguish between what is an object, what is a parking spot, what is a pedestrian, things like this. I'm going to talk about LiDAR. Right now, we currently do need LiDAR. You might have read some articles recently that even Elon Musk is trying to not use LiDAR, and many companies don't want to use LiDAR because they're very expensive. But right now, we still need them. For the time being, we still need them. Radar and ultrasonic sensors, these are sound waves, of course. And then the two areas that are really important for artificial intelligence can be with sensor fusion and data association. Data association is really using traditional machine learning and artificial intelligence techniques, but in the context of using this data with sensor fusion to find out what to classify basically objects or classify free parking spots. So I wanted to give a roadmap. This is a roadmap from the EPOSS. And the reason I want to give this roadmap is because a lot of times we talk about self-driving cars being right around the corner, like maybe 2 or 3 years and we should have them. But in reality, it's quite far away. So the yellow triangles here are the research and development. Green is for demonstration, which means actual technological companies and research companies doing the demonstration and testing the technology. And the blue is for the production and market. So the blue is when it should start becoming available for the general public. And this section, this is technology inside the car. This is just a few examples. There's actually 31 different criteria on the roadmap. That's at the end of the, it's also in a link at the end of the presentation. That shows that if we look down here, what is this? This is fail operationality of the system. This won't be ready until after 2025. And we'll see in a little bit that even sensor fusion, which most people are they're at least familiar with the idea of it within the artificial intelligence and autonomous robotics section that we're talking about, we'll see that it's actually not quite ready. So where are we now? I say, yeah, we're not anywhere really close. We do have anti-lock braking systems for a while, some advanced driving assistant systems, and lane assist and self-parking, because some companies are working on it. We can get it to work in small scale cases, but we still have some challenges. And challenges are, of course, object detection. What is a car? What is a free space? What is a human? We have very noisy data, and we work in non-ideal environments. Because we work in stochastic environments, other vehicles are moving, people can walk in front of a car, there could be a bicycle that's in the parking spot. It looks mostly free based on the dimensions, but however, there's actually something there that we will hit. And if we're looking at the actual levels, we have driving complexity, so this is more difficult, and how fast we're going, our driving velocity. So something like a highway chauffeur, a car that would drive you autonomously, we predict it would be around 2022, something like this, because it doesn't require too much speed if we're driving down our driveway, and it's not too complicated. But something like a highway autopilot, where it really takes control on the freeway or on the highway by itself, this is a more challenging thing. Okay, so this is from Hella, specifically Hella Aglaya, and this is similar to the Udacity flowchart I showed earlier, but this is the specific one for our project that we worked on, and actually the one that they use in their technological designs and things like this. So the sensors that we use are the camera sensors, radar, LiDAR, and SV camera, which we didn't use this, and ultrasonic sensors, which are kind of like radar. They're sound, but you usually use them for shorter distance, mostly just for object detection. Then you have these different type of processes, and then you have to do fusion. And as you see here, fusion is a big part. And it's not just sensor fusion, but it can be the semantic scene interpretation. So this is from semantic segmentation and computer vision. So this is an AI topic. Map fusion, figuring out how to do this properly. Ego fusion, the car is moving, right? So we actually need to be able to try to predict out how is the car moving relative to the environment. So we have a static environment, things are not moving, dynamic environment, things are moving, and we need to be aware of the vehicle state. And the vehicle state is something that the engineer actually has to derive himself. So you actually need to make the state equations, the state space model, based on your actual vehicle. So the location of the LiDAR sensor or the cameras, where are they? This will actually change certain characteristics of your algorithms. Okay, so sensor characteristics. So before we talk about sensors, we want to actually look at how they're kind of different. Cameras, they provide color and contrast. This is good. They can provide high resolution and high range, so they can see very far. And they can work in bright light. However, the important things here are they don't work in the dark, they don't work very good in the snow or the rain, and they don't really work in the fog. And these things are important because some of the technology companies with self-driving cars want to use AI and deep learning to scan the environment. But as we see here, depending on the environment, the camera sensors don't work at all. But at nighttime, something like in the dark, LiDAR can work quite well. And it's very fast. It has a good detection speed. So sometimes it's actually good to use, and in bright light too. In bright light, it works great. So right now, we want to actually try to mitigate the losses from the camera with the LiDAR. And the reason we want to do that is because we don't want to only rely on the radar. So if we only rely on the radar, we might have some bias, and actually radar doesn't work perfectly. The detection speed is pretty fast at short distances, but the distances are not necessarily, it's not necessarily sufficient for real-time systems. So if you need to adapt and have the vehicle do something very quickly, and it hasn't been able to detect the event in time, it will not be able to stop or move in time, which is going to cause an accident. So that's another reason that we look at low velocity profiles right now, and in the future we'll worry more about high velocity profiles. So cameras, we're not going to talk too much about cameras just because everybody knows what they are. There's basically 3 different primary types. This is a picture from, it's not very good resolution. I don't have the slides, the core ones right now still. But basically, as the vehicle went through, it could use computer vision techniques with the, if you look, this is a fisheye camera. We were using a fisheye camera. And then it actually uses classification and labeling to label that this green parking spot is somewhere that we can park. So we have to use deep learning, I said. And why do we need to do that? Well, imagine you have eyes and you can see things around you, but you actually have a processor. Let's say your brain is a processor that is able to recognize and classify objects when you see them. When this slide came up, you could see, oh, this is a cat. This is clearly a cat. I know that this is a cat. But cameras by themselves, a sensor has no idea. It just reports color values. This doesn't mean anything to it. It doesn't mean that this is something where we cannot park or where we can park. So we basically need some type of processing. We need a lot of data for that. So that's where deep learning comes in, especially convolutional neural networks and, well, not just deep learning, but we also need classification. We need regression. We need clustering. We need lots of different models from machine learning. So this little square right here, it's blown up into this, basically a matrix, because this is what the computer sees. The computer or the camera sees just an array of a bunch of values. But as the camera moves, the pixels are going to change, right? Because the location that it's focused on is changing. Also, if the cat moves or another car moves, well, these values are going to change too. And if both are moving, well, this is, it's obvious that there's a lot going on. So now we're not even sure what's going on. So we need some way to be able to look at the distribution of the pixels in this cat. We usually use convolutions for this and figure out, is this a cat or not? It's not always successful, as we'll see. So what are different types of problems that cameras can have? So we can also think about how humans look at this. We call these type of pictures cluttering because there's a cat here and we can see it. But if we wanted to assign this into a data set and classify it based on color, either all of this is going to be a cat or all of this is going to be leaves. It's going to be really difficult to find the cat in the leaves or the cat in the snow. So we call this clutter. Lighting can be different too. Different levels of lighting will actually change the color value of the pixels that you see. And sometimes even with a glare, and glares can be problems for self-driving cars, even though cameras are kind of okay in bright light, it can still cause trouble because when you want to actually do the object recognition. So they work in the bright light, but they might not be able to do object recognition in the bright light. And you can think about this. Imagine anytime you've ever been driving or riding in a vehicle on the freeway, on the highway, and the sun is right in your eyes. Well, if there's a sign approaching you, can you read the sign? Typically, no. I can't read the sign when I'm driving. So you need to use sunglasses or your sun visor. You need some way to try to balance the color contrast. So this is an example of deformation. What that means is, if you look at this cat here, it's laying down in a really awkward way that isn't how you would normally look at a cat. So if you're trying to classify cats based on the shape or the general model that they look like, deep learning is going to have some trouble here. So you need some other criteria to be able to actually identify that this is a cat. Now we as people can see that this is a cat because we have a long history, a long understanding of cats and what they look like in different situations. Obstruction. So this is a type of obstruction or occlusion, it's also called. There's things that are actually hiding the cat. So this cat is in the bushes, we can't really see him. There's a cat under this pillow, we see his tail. But a self-driving car, if there was a car behind, say, a truck, there's a moving car behind a truck or a car behind a set of trash cans. It might not see it. And if that car is moving, it might not see it in time. And this has been a problem for even Tesla recently. So what are the results of this type of deep learning? This image, it's a little blurry on the webinar, but basically these green squares are times where the object or the animal was correctly labeled. So this is a dog, and the convolutional neural network did its thing and sent it through the layers, and yay, this is a dog. But this here is a frog, and it got mislabeled as a cat because the shape is similar, the color, the pixels are similar. So the neural network said that, yeah, this is a cat. But this is actually a frog, so that's a problem. Imagine if you're trying to detect the parking spot and it says, yes, this is an empty parking spot, but actually it's a wall. So there was a wall with an empty parking spot painted on it. If you rely only on cameras, then you're going to think that, okay, this wall with the artwork of a parking spot drawn on it is safe to park. In reality, it's not. And then this is a type of output from convolutional neural networks. So you have your convolution and your rectifying linear units and some pooling. It goes through each step and does some feature extraction. And right now, the fully connected or layers, they're pretty good at detecting, okay, I can see this and this is a car. So there are lots of data sets. There's actually hundreds of data sets, especially if you go onto Coco or do something with ImageNet. Coco is usually the one that we use to learn how to train the network initially, because you also don't have necessarily a lot of videos or pictures of empty parking spots. And you have to figure, how does an empty parking spot look from different angles? If you're standing directly in front of it, of course it looks like a rectangle. But if you're off to an angle a bit, then it's not really, it's more like a parallelogram. Or if you have a fisheye lens, the edges of it are actually rounded, and now it's not a shape that you can't just automatically draw bounding boxes around it. Also, since the camera is moving, right, the car is driving, the car, and you're actually scanning things over a sampling rate, the aberrations from the fisheye camera, because they're rounded, they basically change over time. So you might have something that looks like a rectangle when you're perfectly in front of it, but before you got to it, it was more spherical, and after you got past it, it was also more spherical. And currently, there's no way to automatically create an offset that you can just make bounding boxes for these type of things. So some type of bounding box type criteria in artificial intelligence doesn't work for fisheye lenses, although they're still ideal because we can see with a better range. And of course, this is the ultimate goal of using the camera. So you want to actually say that these green slots are places you can park and the red ones are not. So radar, we'll just briefly discuss that there's 3 types of radar that we primarily use. One of them is for parking. It has an open angle of about 120 degrees, but the distance isn't that great. So it's just a small distance, only 20 meters. Then there's a we call middle range radar, and a high range radar, or long range. And we use radar, and we basically get these point clouds. We also get point clouds for the LiDAR. So we get a bunch of these little dots. We call them pings. The radar returns these pings based on the time of flight, so the distance it takes for it to become reflected. It sends out a sound wave, and then the sound wave is sent back, and you calculate how long, based on the time, what the distance is. It doesn't work on all materials, though. So there's certain type of materials that don't reflect the radar perfectly, which is another reason we want to use LiDAR still. And whenever this happens, you either just don't detect the material at all, or something like, or it's not accurate. You get some really interesting deviations in your point cloud. Over here is an example where we use some machine learning techniques with clustering to actually cluster and say, okay, this is a vehicle. Some of the noise has been filtered out here. You can see it better here. But we're saying that, okay, this is actually some type of car, this is another type of car, and this is another type of car. And each one of these has been given an identification. The radar itself doesn't return anything related to light, so this coloring is based on a labeling task with data association. So one way this is currently being done is with something called DB scan. And DB scan Also uses a type of clustering based on grids. So in the image on the left, there are, well, both images have a pedestrian that's far away, a pedestrian that's, two pedestrians that are next to the sensor, one of the set of vehicles that's near the sensor, and one set of vehicles that's far away from the sensor, and some barrier. So if you use a grid type DB scan, it's just trying to show an example of comparing this new type of DB scan compared to the old one. We can see that for image number 2, which is a pedestrian, we can classify this and cluster it better than just using the typical DB scan. So I wanted to include this because it shows spatial clustering and kind of an idea of how you need to use machine learning and artificial intelligence for radar. So just for one sensor. This is just one sensor. Then this is another type of more grid mapping and free space detection. So the radar has some reflectance points, and then you want to actually assign a probability. So the second image shows like a detection probability. And then what you ultimately want to create is an occupancy grid. So occupancy is whether or not there's a vehicle there or whether or not there's an object there. So we can use these type of things for a self-parking car to find out, okay, the highly red areas, there's a high probability that there's something there. We cannot park there. And if it's blue, or in this case, if it's white, if the background is white, then it's probably safe to park there, or it's at least safe to drive there. We still have to make sure that the car fits into the parking space. So then talking about LiDAR a bit, why LiDAR is good? Well, because they can have massive amounts of data. So this point cloud might send out get a million different data points back. And it's very fast, right? It's LiDAR, so it's laser, it's like the speed of light. Of course, computing it isn't as fast as the speed of light, but still, we want to get the data as quickly as possible. Some bad things about it, though, are that it's quite expensive. So the vehicle that we were working with, the LiDAR was about 60,000 euros, which is actually more than 60,000 US here. It's quite expensive. If you break it, that's a problem, or if someone steals it off the top of your car, that's a problem. But the prices are going down. So as of last month, a couple of companies announced that they will want to mass produce LiDAR sensors for about 5,000 US dollars. However, they still require massive amounts of computational power. You have to be able to process all of these data points. And based on the sampling rate, so if you're going to take this type of sampling rate, let's just pretend it was 1 time per second, you're going to get data points for this often. But really, LiDARs are more than 10 hertz. So you're going to get more than a really bad LiDAR is about 10 hertz, or every 1 second you get 10 images like this. So you need to be able to process these and very quickly and reliably, preferably in real time, especially if you're going to have autonomous driving. Self-parking can be a little bit more flexible, but if you're going to have real self-driving vehicles on the road, you're going to need to increase the computational power or use some type of artificial intelligence and prediction to be able to predict how the environment could change. So we actually do this intrinsically, right? We have this car here, we see that the car moves, and we can predict that this car here is not going to magically be on the other side of the road and 100 meters away. This is an example. So then we have a recent quote here that says, Elon Musk has repeatedly pushed the idea that if humans can perceive and navigate the world using just their eyes and their ears and their brain, then why can't the car? Well, because cars right now, they don't really have a brain. They can't do the same processing and labeling and classification. So we can look at a car and see that it's a car. Even if there's a sign in front of it, we can still say, oh, I think there's a car behind there. But computers are not really intelligent. They aren't able to just distinguish between the two. So yeah, we're not there yet. And in general, this is the example. This is the LiDAR scanners on top of the vehicle on the top image. And it basically has some distance to a target. And based on the elapsed time, how long it takes light to get there and become reflected back, the time of flight, tells us about the environment. The image on the bottom is an example of for parked cars and trees. How does the 3D LiDAR detection look like? And in the bottom left corner, we see this is actually what's called slicing. They do slicing and show the images of the pedestrians, how they look. So then we talk about sensor fusion. So this is actually more of my specialty. And I'll show you how sensor fusion can also be done with artificial intelligence. And it's also the algorithms that we talk about are maybe ones that you've learned about before or that you will learn about later. So we want to combine the sensory data. And when we do this, we can get more accurate estimations. And also, it alleviates the weaknesses found in standalone sensors. That means that the camera doesn't work in the nighttime very well when it's black, but the LiDAR can, or the radar can. And basically, when we combine the good things from the different sensors, then we get a much better estimate of that this is actually a person and not a parking spot. This is just a general example of having multiple types of sensors. So these long pink ones here, the long and mid-range radars, the short-range radars are these little green fans. And this little dotted line here, this is the detectable site of a person, the night vision of a person at nighttime. So as you can see, if we use sensors appropriately, then we can get a much bigger range of our environment and know much better about our surroundings. So for something like a self-parking car project, you need to seek out the parking self-parking car. You need to seek out the parking spaces. Which ones are empty? Which ones are full? And so we confirm the availability. Yes, it's good. And then we have to ask ourselves: are we concerned with detecting moving objects? Because this adds a whole another level of complexity. For our project, we actually wanted to try to not have any moving objects because this adds a lot of challenges to the project. So we just looked at parking spots where there were no incoming vehicles or pedestrians or other moving objects. And then you also need to meet the real-time functional and quality requirements. So this is basically a real-time system. And if you don't perform perfectly in real time, if you have any type of lag, delay, drift, or jitter, then you might hit something and you didn't even know it, just because you're waiting for an update. You can have event-driven or time-driven systems, but in general, when you have something with sampling rates, and the sensors down here in the design considerations, they have asynchronous sampling rates. That means that the rate that the LiDAR and the rate that the camera data is coming in is not the same. So you need to synchronize these somehow, or try to take some type of estimate. And the data is very nonlinear, especially for radar. So this is more details about the case study that we did, the project we worked on. We had to select appropriate algorithms and apply based on the data in the model. And we need to classify objects and assign object IDs, which is not really, we thought it would be trivial at first, and it turns out that it's not. And then we decided to meet all the criteria, we wanted to find out at least where we cannot safely park. Because it started to become challenging with the fisheye camera to figure out, can we actually park here? So instead of guaranteeing that we could park here, we guaranteed that we wouldn't park somewhere that wasn't safe. So safety is always first in autonomous technology. So with robotics or self-driving cars, safety should always be first, and then science. So you remember before we had these sensor characteristics. These are each one for the different sensors. And then when we put them together, we get something like this. So this is a result of sensor fusion. We have now a lot of good things. The cost here, it's a low number here because this is quite expensive. We're approaching 60 or 70,000 euros now. And the size, I don't know if you've ever seen a radar or a LiDAR sensor on top of a vehicle, but they are quite big. They also take up a lot of space in the trunk. So the trunk, the back end of the vehicle is going to be completely filled with basically a giant computer that can communicate and process this data. So for us, we used the extended Kalman filter, and we had to use the extended Kalman filter. A regular Kalman filter isn't sufficient because the data is not linear. We have a high measurement frequency, so the sampling rate is very high. And we use a Jacobian for local linearity. On the next image, I have an example of locality of making things linear. You can also use multiple instances of the EKF, so each sensor can have its own Kalman filter. If you're familiar with the unscented Kalman filter, it turns out that you actually cannot simply fuse everything together. And this is conflicting with some of the literature. If you read on ResearchGate or some other publications, they say, yeah, unscented Kalman filter is just fine. But it turns out in practice and use, it has a lot of additional challenges and requires a lot more computation. So for the EKF, we're looking at sparseness in the matrices, which is basically means we're looking for zeros. If we can remove or ignore the zeros, then we can compute things much faster. So we have this Gaussian distribution. This is basically a probability distribution function. And if we use a derivative on it, we are going to get something like this image on the right, where the distribution is not a Gaussian anymore. And that's a problem because now we're not able to actually actively predict anything. Basically, the Gaussian distribution, and this is what happens if you just differentiate a Kalman filter. The highly nonlinear and stochastic data, it just returns a bunch of basically garbage. But if we use the Jacobian, we can do a linear approximation. So then when we differentiate our Gaussian distribution here, we get another Gaussian distribution, which is what we want. And why do we need to do this type of thing? So what's the problem? On the left side, we have the results of the radar. And we've actually clustered, so we clustered these and we got some different points. Okay, so they're clustered. On the right side, we have output from the LiDAR sensors, and we've also kind of clustered them. But if you look at them, you can't really tell what's going on. What is a car, what's not? How do I identify things? How is the radar and the LiDAR even related? And we don't know. So what we want to do is we want to track how things change over time. So this is data association. We basically want to track and assign multiple object IDs. The bounding boxes for each type of, if we go back, the bounding boxes here are not the same size. So the bounding boxes for the radar and the LiDAR are not the same size, so you can't just overlap them. They also don't match with the camera. The camera's bounding boxes are also different. So you need some way to handle this. And we still have noise too. So we used nearest neighbors, and most machine learning students are familiar with nearest neighbors. We use actually what's called global nearest neighbors, and it basically acts like a filter. So we have to figure out, is the distribution deterministic or probabilistic? How does it change over time? And we call this evolution. And we basically want to track how do objects change over time and which ones are meaningful objects, and then how can we assign IDs to them. So then you assign IDs to them, and you give some distribution, and you use your machine learning algorithm to try to predict and classify what's the probability this is an object. This is just a general fusion flowchart. So we have some weighted average of the LiDAR and the radar. This is after we've determined that a nearest neighbor is found. And we just basically go through this list after we detect a new object and we want to add it to our list and then compare it. So if we detect it with the radar, we want to compare it with the LiDAR and so on. And this is just an example of the state space that we made. So we have all of our sensor measurements. If the list is not empty, then we calculate the nearest neighbor. If a neighbor exists, then we apply the Kalman filter based on that. And you can use the Kalman filter for machine learning as well. So for the outlook, for sensor fusion and AutoSAR and